Hello all. Let's start with isothermal operation and adiabatic operation. So I would be differentiating isothermal operation and adiabatic operation on the basis of their properties. So first of all, let's start with isothermal operation. So isothermal operation is a change in pressure and volume of a gas without any change in its temperature. So that means there won't be any temperature change inside the thermodynamical system. P will be changing, V will be changing, but the temperature change in this case will be constant. T is constant in this condition, but P is changing and V is changing. So if there is change in pressure and volume, then we can say that it is an isothermal operation without changing temperature. So there should not be any change in temperature, but there should be change in pressure and volume. Then only we can consider it as an isothermal operation. So let us now know about two essential conditions for a perfect isothermal change. So there are two essential conditions. The first should be the walls of the container we are taking, the thermodynamical system. It should be perfectly conducting. So if it will be perfectly conducting, that means it can allow free exchange of heat between gas and its surroundings. So it should be perfectly conducting. The walls should be perfectly conducting. This is the first condition. Now the second condition is that the process of compression or expansion should be very slow. So this should be a very slow process. Then only we can consider it as isothermal operation. The first is the walls of the container must be perfectly conducting to allow free exchange of heat between gas and its surrounding. And the second should be the process of compression or expansion should be very slow. Now, what would be the examples for isothermal change? So in this we can consider two examples, that is melting and another could be boiling. These are very simplified examples for isothermal change. Now, as you can see on your screen that we have a PV graph here. Now, as you all know that for ideal gas, we have equation PV equal nRT. Now, as you know that the temperature in the case of isothermal change is constant, so therefore my right hand side will be a constant. So in this case, it is written as PV equal to constant. Now, as you can see, I have drawn three curves here which are at different temperature. One is at T1, one is at T2 and one is at T3. It is in the order T3 is greater than T2 is greater than T1. That means if the temperature is more, the curve will be away from PV graph, and if the temperature is less, it will be more closer to PV graph. Now, the next thing, let us come on to the next part, that is specific heat of gas, that is denoted by C. Now, as you know, in an isothermal change, we know that T is constant. So this basically means if T is constant, then my del T, the change in temperature, will be 0. So the specific heat is given by del Q, that is heat content over mass del T. Now, as you know that the numerator is 0, that means it will be infinity. So specific heat of gas in case of isothermal, it will be infinity. Now let's start with adiabatic operation. So in the adiabatic operation, we have a change in pressure and volume of a gas, and in this case we have temperature change as well. So three things are changing here, that is pressure, volume and temperature as well. Then only we can consider it as a adiabatic operation. Now the difference in adiabatic and isothermal. First difference in adiabatic and isothermal operation will be that in this case these three all are changing, and in the case of isothermal operation pressure and volume changes. Now let us consider the two essential conditions for a perfect adiabatic changes. Now in this case the walls of the container must be perfectly non-conducting. They should be non-conducting in order to prevent any heat exchange between the gas and its surrounding. So they must be non-conductors to prevent any exchange of heat between gas and its surrounding. Now the second thing is the process of compression or expansion should be very sudden. Like in the case of isothermal operation, it was a slow process. It should be a slow process. Whereas in this case, it should be a sudden process. Like for example, we have two examples for this case. They are very general, like expansion of heat gases that can be considered as adiabatic change, and the next could be expansion of steam in cylinders. So that can be again considered as adiabatic change. So expansion of steam in cylinders. Now the next is as you know that in ideal condition we have PV equal nRT. Now in this case we consider it as PV gamma equal K, and gamma here is specific heat of gas at constant pressure over specific heat of the gas at constant volume. So we need to denote it specific heat of the gas at constant pressure. The next is over specific heat of the gas at constant volume. Now, as you know, the equation for ideal gas is PV equal RT. Now we can get the value of P from here. That will be RT over V. Now we'll be putting this value, pressure value, into the equation of adiabatic. So it will be RT V gamma equal K. So it can be written as RT V gamma minus 1 K. And it can be again, we can bring this R to the right hand side, as you know it is a constant. So it will be K by R, which is a constant. That means this is the relation between T and V. So TV gamma minus 1 equal constant. So remember the relation between T and V in the case of adiabatic change is TV gamma minus 1 equal to constant. Relation between T and V. Now next thing. Next thing is that in as you know again we need to change we need to bring a new one like PV equal to RT. So it will be V equal RT over P. Now I will be replacing, as you know, the adiabatic change equation is PV gamma mine equal K. So I would be now equating the value of V into it. So this will be RT P gamma equal K. So it will be P gamma minus 1 R gamma T gamma equal K. Now again bringing this constant to right hand side. So my equation will be P gamma minus 1 T gamma equal constant. That means this is my equation, and you can say this is the relation between pressure and temperature under adiabatic changes. Now we need to derive the C for it again. Like as we did in the case of isothermal change, we need to do the same. for adiabatic. Now, as you know, in the case adiabatic, we have del Q as 0 because there is no heat content change. So, in this case, C will be equal to 0 because as you know it is directly proportional to del Q, so it will be 0. So in this case the specific heat of gas is 0. Now let us start with the differentiation of adiabatic and isothermal change. So this will be very easy as we have already done the basics. So let's draw the table. Isothermal and adiabatic. So in the first isothermal, the temperature is constant, that is del T equals 0. Now in the case of adiabatic, it will be del Q equals 0. Second, in this case, the system is thermally conducting, the isothermal. System is thermally conducted. And in the case of adiabatic, it is non-thermal, or you can say it is insulated. Now the third one, in this case changes occur very slowly. In the adiabatic it is sudden process. The last one, the specific heat in the case of isothermal is infinity and the specific heat in the case of adiabatic is 0. So this is the difference between isothermal and adiabatic. Now we'll start with internal energy in the next section. Thank you for watching.